Statements, hypotheses, or theories have falsifiability or refutability if there is the inherent possibility that they can be proven false. They are falsifiable if it is possible to conceive of an observation or an argument which could negate them. In this sense, falsify is synonymous with nullify, meaning to invalidate or show to be false. For example, the universal generalization that all swans are white is falsifiable since it is logically possible to falsify it by observing a single black swan. Thus, the term falsifiability is sometimes synonymous to testability. Some statements, such as "it will be raining here in 1 million years," are falsifiable in principle, but not in practice. The concern with falsifiability gained attention by way of philosopher of science Karl Popper's scientific epistemology falsificationism. Popper stresses the problem of demarcation, distinguishing the scientific from the unscientific, and makes falsifiability the demarcation criterion, such that what is unfalsifiable is classified as unscientific, and the practice of declaring an unfalsifiable theory to be scientifically true is pseudoscience. Overview. The classical view of the philosophy of science is that it is the goal of science to prove hypotheses like all swans are white or to induce them from observational data. Popper argued that this would require the inference of a general rule from a number of individual cases, which is inadmissible in deductive logic. For however, if one finds one single swan that is not white, deductive logic admits the conclusion that the statement that all swans are white is false. Falsificationism thus strives for questioning, for falsification, of hypotheses instead of proving them. For a statement to be questioned using observation, it needs to be at least theoretically possible that it can come into conflict with observation. A key observation of falsificationism is thus that a criterion of demarcation is needed to distinguish those statements that can come into conflict with observation and those that cannot. Chorlton, 2012. Popper chose falsifiability as the name of this criterion. My proposal is based upon an asymmetry between verifiability and falsifiability, an asymmetry which results from the logical form of universal statements. For these are never derivable from singular statements, but can be contradicted by singular statements. Karl Popper, The Logic of Scientific Discovery, p. 19. Popper stressed that unfalsifiable statements are important in science. 6. Contrary to intuition, unfalsifiable statements can be embedded in and deductively entailed by falsifiable theories. For example, while all men are mortal is unfalsifiable, it is a logical consequence of the falsifiable theory that every man dies before he reaches the age of 150 years. Similarly, the ancient metaphysical and unfalsifiable idea of the existence of atoms has led to corresponding falsifiable modern theories. Popper invented the notion of metaphysical research programs to name such unfalsifiable ideas. In contrast to positivism, which held that statements are meaningless if they cannot be verified or falsified, Popper claimed that falsifiability is merely a special case of the more general notion of criticizability, even though he admitted that empirical refutation is one of the most effective methods by which theories can be criticized. Criticizability, in contrast to falsifiability, and thus rationality, may be comprehensive, i.e., have no logical limits, though this claim is controversial, even among proponents of Popper's philosophy and critical rationalism. Naive falsification. Two types of statements, observational and categorical. In work beginning in the 1930s, Popper gave falsifiability a renewed emphasis as a criterion of empirical statements in science. Popper noticed that two types of statements are of particular value to scientists. The first are statements of observations, such as "there is a white swan." Logicians call these statements singular existential statements, since they assert the existence of some particular thing. They are equivalent to a predicate calculus statement of the form, "there exists an X such that X is a swan, and X is white." The second are statements that categorize all instances of something, such as all swans are white. Logicians call these statements universal. They are usually parsed in the form, for all x, if x is a swan, then x is white. Scientific laws are commonly supposed to be of this type. One difficult question in the methodology of science is, how does one move from observations to laws? How can one validly infer a universal statement from any number of existential statements? Inductivist methodology supposed that one can somehow move from a series of singular existential statements to a universal statement. That is, that one can move from "this is a white swan," "that is a white swan," and so on, to a universal statement such as "all swans are white." This method is clearly deductively invalid, since it is always possible that there may be a non-white swan that has eluded observation, and, in fact, the discovery of the Australian black swan demonstrated the deductive invalidity of this particular statement. Inductive categorical inference. Popper held that science could not be grounded on such an inferential basis. He proposed falsification as a solution to the problem of induction. Popper noticed that although a singular existential statement such as "there is a white swan" cannot be used to affirm a universal statement, it can be used to show that one is false. The singular existential observation of a black swan serves to show that the universal statement "all swans are white" is false in logic. This is called modus tollens. "There is a black swan" implies there is a non-white swan, which, in turn, implies there is something that is a swan and that is not white. Hence "all swans are white" is false, because that is the same as "there is nothing that is a swan and that is not white." One notices a white swan. From this one can conclude, at least one swan is white. From this, one may wish to conjecture, all swans are white. It is impractical to observe all the swans in the world to verify that they are all white. Even so, the statement "all swans are white" is testable by being falsifiable. For, if in testing many swans, the researcher finds a single black swan, then the statement "all swans are white" would be falsified by the counterexample of the single black swan. Deductive falsification. Although the logic of naive falsification is valid, it is rather limited. Nearly any statement can be made to fit the data, so long as one makes the requisite compensatory adjustments. Popper drew attention to these limitations in The Logic of Scientific Discovery in response to criticism from Pierre Duhem. W. V. Quine expounded this argument in detail, calling it confirmation holism. To logically falsify a universal, one must find a true falsifying singular statement. But Popper pointed out that it is always possible to change the universal statement or the existential statement so that falsification does not occur. On hearing that a black swan has been observed in Australia, one might introduce the ad hoc hypothesis, "all swans are white except those found in Australia," or one might adopt another, more cynical view about some observers: Australian bird watchers are incompetent. Thus, naive falsification ought to, but does not, supply a way of handling competing hypotheses for many subject controversies, for instance conspiracy theories and urban legends. People arguing that there is no support for such an observation may argue that there is nothing to see, that all is normal, or that the differences or appearances are too small to be statistically significant. On the other side are those who concede that an observation has occurred and that a universal statement has been falsified as a consequence. Therefore, naive falsification does not enable scientists, who rely on objective criteria, to present a definitive falsification of universal statements. Falsificationism. Naive falsificationism is an unsuccessful attempt to prescribe a rationally unavoidable method for science. Sophisticated methodological falsification, on the other hand, is a prescription of a way in which scientists ought to behave as a matter of choice. The object of this is to arrive at an incremental process whereby theories become less bad. Naive falsification considers scientific statements individually. Scientific theories are formed from groups of these sorts of statements, and it is these groups that must be accepted or rejected by scientists. Scientific theories can always be defended by the addition of ad hoc hypotheses. As Popper put it, a decision is required on the part of the scientist to accept or reject the statements that go to make up a theory or that might falsify it. At some point, the weight of the ad hoc hypotheses and disregarded falsifying observations will become so great that it becomes unreasonable to support the base theory any longer, and a decision will be made to reject it. In place of naive falsification, Popper envisioned science as progressing by the successive rejection of falsified theories, rather than falsified statements. Falsified theories are to be replaced by theories that can account for the phenomena that falsified the prior theory, that is, with greater explanatory power. For example, Aristotelian mechanics explained observations of everyday situations, but were falsified by Galileo's experiments, and were replaced by Newtonian mechanics, which accounted for the phenomena noted by Galileo, and others. Newtonian mechanics' reach included the observed motion of the planets and the mechanics of gases. The Jungian wave theory of light, i.e., waves carried by the luminiferous ether, replaced Newton's, and many of the classical Greeks, particles of light, but in turn was falsified by the Michelson-Morley experiment and was superseded by Maxwell's electrodynamics and Einstein's special relativity, which did account for the newly observed phenomena. Furthermore, Newtonian mechanics applied to the atomic scale was replaced with quantum mechanics, when the old theory could not provide an answer to the ultraviolet catastrophe, the Gibbs Paradox, or how electron orbits could exist without the particles radiating away their energy and spiraling towards the center. Thus the new theory had to posit the existence of unintuitive concepts such as energy levels, quanta, and Heisenberg's uncertainty principle. At each stage, experimental observation made a theory untenable, i.e., falsified it, and a new theory was found that had greater explanatory power, i.e., could account for the previously unexplained phenomena, and as a result, provided greater opportunity for its own falsification. Criterion of Demarcation. Popper uses falsification as a criterion of demarcation to draw a sharp line between those theories that are scientific and those that are unscientific. It is useful to know if a statement or theory is falsifiable, if for no other reason than that it provides us with an understanding of the ways in which one might assess the theory. One might at the least be saved from attempting to falsify a non-falsifiable theory, or come to see an unfalsifiable theory as unsupportable. Popper claimed that, if a theory is falsifiable, then it is scientific. The Popperian criterion excludes from the domain of science not unfalsifiable statements but only whole theories that contain no falsifiable statements, thus it leaves us with the Duhamian problem of what constitutes a whole theory as well as the problem of what makes a statement meaningful. Popper's own falsificationism, thus, is not only an alternative to verificationism, it is also an acknowledgement of the conceptual distinction that previous theories had ignored. Verificationism. In the philosophy of science, verificationism, also known as the verifiability theory of meaning, holds that a statement must, in principle, be empirically verifiable in order that it be both meaningful and scientific. This was an essential feature of the logical positivism of the so-called Vienna Circle that included such philosophers as Moritz Schlick, Rudolf Carnap, Otto Neurath, the Berlin philosopher Hans Reichenbach, and the logical empiricism of A.J. Ayer. Popper noticed that the philosophers of the Vienna Circle had mixed two different problems, that of meaning and that of demarcation, and had proposed in verificationism a single solution to both. In opposition to this view, Popper emphasized that there are meaningful theories that are not scientific, and that, accordingly, a criterion of meaningfulness does not coincide with a criterion of demarcation. Thus, Popper urged that verifiability be replaced with falsifiability as the criterion of demarcation. On the other hand, he strictly opposed the view that non-falsifiable statements are meaningless or otherwise inherently bad, and noted that falsificationism does not imply it. Use in courts of law. Judge William Overton used falsifiability in the McLean v. Arkansas ruling in 1982 as one of the criteria to determine that creation science was not scientific and should not be taught in Arkansas public schools as such. It can be taught as religion. The argument was presented by philosopher Michael Ruse, who defined the characteristics which constitute science as explanatory, testable, and tentative, the latter of the three being another term for falsifiability. In his conclusion related to this criterion, Judge Overton stated that while anybody is free to approach a scientific inquiry in any fashion they choose, they cannot properly describe the methodology as scientific, if they start with the conclusion and refuse to change it regardless of the evidence developed during the course of the investigation. United States law also enshrined falsifiability as part of the Daubert standard set by the United States Supreme Court for whether scientific evidence is admissible in a jury trial. Criticisms. Contemporary philosophers. Many contemporary philosophers of science and analytic philosophers are strongly critical of Popper's philosophy of science. Popper's mistrust of inductive reasoning has led to claims that he misrepresents scientific practice. Bartley in 1978 claimed, "Sir Karl Popper is not really a participant in the contemporary professional philosophical dialogue, quite the contrary, he has ruined that dialogue. If he is on the right track, then the majority of professional philosophers the world over have wasted or are wasting their intellectual careers." The gulf between Popper's way of doing philosophy and that of the bulk of contemporary professional philosophers is as great as that between astronomy and astrology. W. W. Bartley in Philosophia 6, 1976. Rafe Champion said, "Popper's ideas have failed to convince the majority of professional philosophers because his theory of conjectural knowledge does not even pretend to provide positively justified foundations of belief. Nobody else does better, but they keep trying, like chemists still in search of the philosopher's stone or physicists trying to build perpetual motion machines." Rafe Champion agreeing to disagree, Bartley's Critique of Reason 1985. David Miller. "What distinguishes science from all other human endeavors is that the accounts of the world that are best, mature sciences deliver are strongly supported by evidence, and this evidence gives us the strongest reason to believe them. That anyway is what is said at the beginning of the advertisement for a recent conference on induction at a celebrated seat of learning in the UK. It shows how much critical rationalists still have to do to make known the message of Logic der Forschung concerning what empirical evidence is able to do and what it does." David Miller, Some Hard Questions for Critical Rationalism 2011. Kuhn and Lakatos. Whereas Popper was concerned in the main with the logic of science, Thomas Kuhn's influential book The Structure of Scientific Revolutions examined in detail the history of science. Kuhn argued that scientists work within a conceptual paradigm that strongly influences the way in which they see data. Scientists will go to great length to defend their paradigm against falsification, by the addition of ad hoc hypotheses to existing theories. Changing a paradigm is difficult, as it requires an individual scientist to break with his or her peers and defend a heterodox theory. Some falsificationists saw Kuhn's work as a vindication, since it provided historical evidence that science progressed by rejecting inadequate theories, and that it is the decision, on the part of the scientist, to accept or reject a theory that is the crucial element of falsificationism. Foremost amongst these was Imre Lakatos. Lakatos attempted to explain Kuhn's work by arguing that science progresses by the falsification of research programs rather than the more specific universal statements of naive falsification. In Lakatos' approach, a scientist works within a research program that corresponds roughly with Kuhn's paradigm. Whereas Popper rejected the use of ad hoc hypotheses as unscientific, Lakatos accepted their place in the development of new theories. Feyerabend. Paul Feyerabend examined the history of science with a more critical eye, and ultimately rejected any prescriptive methodology at all. He rejected Lakatos' argument for ad hoc hypothesis, arguing that science would not have progressed without making use of any and all available methods to support new theories. He rejected any reliance on a scientific method, along with any special authority for science that might derive from such a method. Rather, he claimed that if one is keen to have a universally valid methodological rule, epistemological anarchism or anything goes would be the only candidate. For Feyerabend, any special status that science might have derives from the social and physical value of the results of science rather than its method. Sokal and Brickmont. In their book Fashionable Nonsense, published in the UK as Intellectual Impostures, the physicists Alan Sokal and Jean Brickmont criticized falsifiability on the grounds that it does not accurately describe the way science really works. They argue that theories are used because of their successes, not because of the failures of other theories. Their discussion of Popper, falsifiability, and the philosophy of science comes in a chapter entitled Intermezzo, which contains an attempt to make clear their own views of what constitutes truth, in contrast with the extreme epistemological relativism of postmodernism. Sokal and Brickmont write, when a theory successfully withstands an attempt at falsification, a scientist will, quite naturally, consider the theory to be partially confirmed and will accord it a greater likelihood or a higher subjective probability. But Popper will have none of this. Throughout his life he was a stubborn opponent of any idea of confirmation of a theory, or even of its probability. The history of science teaches us that scientific theories come to be accepted above all because of their successes. Sokal and Brickmont 1997, 6-2f. They further argue that falsifiability cannot distinguish between astrology and astronomy, as both make technical predictions that are sometimes incorrect. David Miller, a contemporary philosopher of critical rationalism, has attempted to defend Popper against these claims. Miller argues that astrology does not lay itself open to falsification, while astronomy does, and this is the litmus test for science. Economics. Karl Popper argued that Marxism shifted from falsifiable to unfalsifiable. Some economists, such as those of the Austrian school, believe that macroeconomics is empirically unfalsifiable and that thus the only appropriate means to understand economic events is by logically studying the intentions of individual economic decision-makers, based on certain fundamental truths. Prominent figures within the Austrian school of economics Ludwig von Mises and Friedrich Hayek were associates of Karl Popper's, with whom they co-founded the Mont Pelerin Society. Evolution. Main article, Objections to Evolution, Unfalsifiability. Numerous examples of potential, indirect, ways to falsify common descent have been proposed by its proponents. J.B.S. Haldane, when asked what hypothetical evidence could disprove evolution, replied fossil rabbits in the Precambrian era. Richard Dawkins adds that any other modern animal, such as a hippo, would suffice. Karl Popper at first spoke against the testability of natural selection but recanted, "I have changed my mind about the testability and logical status of the theory of natural selection, and I am glad to have the opportunity to make a recantation." Young Earth creationism. Much of the criticism against young Earth creationism is based on evidence in nature that the Earth is much older than adherents believe. Confronting such evidence, some adherents make an argument, called the Omphalos Hypothesis, that the world was created with the appearance of age, e.g., the sudden appearance of a mature chicken capable of laying eggs. This hypothesis is non-falsifiable since no evidence about the age of the Earth, or any astronomical feature, can be shown not to be fabricated during creation. Historicism. Theories of history or politics that allegedly predict future events have a logical form that renders them neither falsifiable nor verifiable. They claim that for every historically significant event, there exists an historical or economic law that determines the way in which events proceeded. Failure to identify the law does not mean that it does not exist, yet an event that satisfies the law does not prove the general case. Evaluation of such claims is at best difficult. On this basis, Popper fundamentally criticized historicism in the sense of any preordained prediction of history and argued that neither Marxism nor psychoanalysis was science, although both made such claims. Again, this does not mean that any of these types of theories is necessarily incorrect. Popper considered falsifiability a test of whether theories are scientific, not of whether propositions that they contain or support are true. Mathematics. Many philosophers believe that mathematics is not experimentally falsifiable, and thus not a science according to the definition of Karl Popper. However, in the 1930s Gödel's incompleteness theorems proved that there does not exist a set of axioms for mathematics which is both complete and consistent. Karl Popper concluded that most mathematical theories are, like those of physics and biology, hypothetico-deductive. Pure mathematics therefore turns out to be much closer to the natural sciences whose hypotheses are conjectures, than it seemed even recently. Other thinkers, notably Imre Lakatos, have applied a version of falsificationism to mathematics itself. Like all formal sciences, mathematics is not concerned with the validity of theories based on observations in the empirical world, but rather, mathematics is occupied with the theoretical, abstract study of such topics as quantity, structure, space, and change. Methods of the mathematical sciences are, however, applied in constructing and testing scientific models dealing with observable reality. Albert Einstein wrote, "One reason why mathematics enjoys special esteem, above all other sciences, is that its laws are absolutely certain and indisputable, while those of other sciences are to some extent debatable and in constant danger of being overthrown by newly discovered facts." Quotations. Albert Einstein is reported to have said something that can be paraphrased into, "No amount of experimentation can ever prove me right, a single experiment can prove me wrong." Popper said, "The criterion of the scientific status of a theory is its falsifiability, or refutability, or testability." Popper cited in Klemp 1998.
Please subscribe and thanks for watching.